Okay, let me write the limit comparison test first, and then we'll look at it, okay? So the limit comparison test says that suppose that the series A sub n and series B sub n. Now, what we're doing is we're getting more advanced. We're starting to realize that we don't necessarily have to start a series at 1 or at 0, at 2, or at 25 or whatever. So we're just going to write it as the series A sub n and B sub n, and then where they start is where they start, etc. Okay, so these guys are series with positive terms. It's important. Now, what that should also tell you is that there's no such thing as a Rosetta Stone comparison or test for convergence. All right, the one test for convergence that we actually have that works every time is that if a series is going to converge, then the limit of a sub n at infinity has to be 0. That's the one that has to be satisfied every single time. Otherwise, you're going to use different tests at different times. It's very much kind of like integration techniques where we use different skills at different times. We use substitution, we used parts, we used the Fantastic 15, et cetera, et cetera. Okay, so sorry about that. All right, now our series with positive terms. Then, if the limit as n goes to infinity of a sub n over b sub n equals a constant that's greater than 0. It has to be greater than 0, right? Because they're positive terms, you would hope anyway. Then, and here's the power of it, either a sub n and b sub n, the series, both converge or both diverge. Now, just sit with that for a second. Sit with that for just a second. Why would that be true? Let's do exactly this guy right here. I want to determine, let's go back, and we're going to say, instead of n equals 1 to infinity, let's go n equals 152 to infinity, right? It doesn't really matter where we start these things, all right? Over n squared plus 3n plus 2. I want to figure out if this thing converges or diverges. Well, hopefully you're already realizing, not only, well, for a number of reasons, you're realizing it already converged by the comparison test to 1 over n squared. But if you look close, at infinity, 1 over n squared plus 3n plus 2 starts behaving a whole heck of a lot like 1 over n squared. At infinity, these extra terms don't start contributing much to the value because this guy's getting out of hand so fast. So what the limit comparison test says is, okay, this thing smells like a 1 over n squared out at infinity, so let's compare it to 1 over n squared and see what happens. So here's what you do. You say by the limit comparison test, which is LCT, by LCT, the limit. Oh, wait, allow me to I need to interject here a little bit. What you want to do is you want to pick a series that you know converges. Remember, we know that this series converges because it's P series with P equals 2. You want to pick the series that you know converges and set this equal to A sub n. It doesn't matter if you let it be B sub n or A sub n, but the mathematics gets prettier if you let the simplest thing be the numerator. If you let it be the denominator, sometimes it can get a little, just a little bit funky. You'll see why here in just a sec. Take the limit, and then goes to infinity of, now it's if this is A sub n, 1 over n squared is A sub n, then I'm going to call this sequence B sub n. So I'm going to do 1 over n squared over 1 over n squared plus 3n plus 2. And this turns into the limit as n goes to infinity of n squared plus 3n plus 2 over n squared. Now, we've dealt with this a million times. Look at this. I could even divide n by n squared and take the limit at infinity, and guess what I get? I get 1. So, by limit comparison test, the limit since the limit as n goes to infinity of a sub n over b sub n equals 1, and the sum as n goes from 1 to infinity of 1 over n squared converges, we know the sum as n goes from, whoops, I did 152, right? 152 to infinity. It was 152 to infinity of 1, I outsmart Alec myself, over 3n plus 2 converges as well. Now, there may be this little thing in the back of your brain going, well, okay, sweet, we know it converges. What does it converge to? The answer to that is, on the face of it, we don't know. Now, there are numerical techniques that we're going to talk about in class, okay? Excuse me, that are going to help me out with this, okay? So, that are going to help me approximate what it converges to. But for right now, all that we're concerning ourselves with is, does it converge and does it diverge? Because if it doesn't converge and I'm spending a bunch of time trying to figure out numerically what it's converging to, I can waste a whole lot of time. So for right now, in class, tomorrow we'll discuss some numerical techniques to start to figure out what this thing might converge to. Because on the face of it, the only convergent series that we know what it goes to is the geometric, right? That's the only one that we know the sum equals blah. All right. Now, I'm going to do one more of these, and then I'm done. Okay? I promise. What if I have this guy? If I do the sum as n goes from, now, quit being a smart aleck. Okay? If I have the sum as n goes from 1 to infinity of 1 over, let's do the square root of 4n plus 1 plus 2n squared. Okay? Now, again, you're going through your checklist, not geometric, not a p-series, bummer. Wow, it doesn't really even look like a p-series, does it? I don't know what to compare it to. Oh, what a mess. And especially like if I have like a negative, if I got a minus here or something, that can be a little daunting, because do I end up with positive, negative terms? Oh no, well, it's obvious that I end up with positive terms, true? So what I do is if I think that I'm stuck, but I think that the limit comparison test might work well, actually, what I do is I look at this thing and I think about what it does out at infinity. 4n minus 1 plus 2n squared. Now clearly, as n goes to infinity, do you agree that this thing has no choice but to go to 0? It's obvious. But really what it goes to, remember, all these extra little terms out at infinity disappear and they become kind of useless. All right, so what this thing appears to turn into is 1 over the square root of 2n squared, which if you think about that, what that is it's 1 over 2n. Since n is positive, I don't have to worry about the absolute value of n, right? Now, what I just gave myself was a series that I know, well, this is a sequence, but when I put it in series form, I know that this thing is either going to converge or diverge. What does this series, let's be a little more fancy, 1/2 or 1 over 2n as n goes from 1 to infinity. What does that do? Well, if the 2 frightens you, pull it out, right? We have rules about sums where I can pull constants out, very much like integrals and derivatives and all that stuff. Oh my goodness, look at that. It's the harmonic. It diverges. Which implies that since out at infinity, this thing right here behaves very much like this thing right here, we're going to use the limit comparison test just really quickly to show that it diverges. Because it smells like 1 over 2n. So, you ready? The limit as n goes to infinity of, remember, take this guy first. However, I'm going to show you a trick right here. It'll make your lives a lot simpler. Instead of using this as my a sub n, I'm going to use this form of it. I'm going to let this be a sub n. They're the same thing. There's no difference. There's absolutely no difference. I don't have to worry about absolute values because n is always positive. There's no, oh, that should be a root 2. Sorry, you guys. I guess there is a difference. So that's a root 2, and that's a root 2, but we know what we're looking at. Sorry about that. All right, watch. I'm even going to get rid of the root 2 because I don't really care about it. It's a constant that can be pulled out anyway. I'm going to leave it in this form. I'm going to let the limit as n goes to infinity of a sub n over b sub n be 1 over the square root of n squared. That's a sub n. And then I'm going to divide that by 1 over the square root of 4n minus 1 plus 2n squared. And this is equal to the limit as n goes to infinity of, now this is going to be the square root of 4n minus 1 plus 2n squared over the square root of n squared. Now again, you may be going, well, Ripley, wait a second, why did you rewrite it this way? That seems a little silly, minus the root 2, of course. Well, look, the square root, remember, I'll write this over here, the square root of a, oh crap, let's write it over here. The square root of a over the square root of b can be written as big square root of a over b. So watch what happens. This becomes big square root of 4n over n squared plus, minus 1 over n squared. Oh, I'm getting all kinds of lazy. Let me rewrite this because I don't want to get you guys too screwed up here. This equals the limit as n goes to infinity of big square root of 4n over n squared minus 1 over n squared plus 2n squared over n squared, right? Well, clearly, those cancel, and I end up with 2 right there. As n goes to infinity, this guy goes to 0, right? N squared is bigger than n. This guy goes to 0, and guess what we get? We get root 2. Everything else canceled or went to 0. Last I checked, root 2 is greater than 0. Right? Now, we have to do a little more lawyering here. All right? We have to do a little more writing, hemming, and hawing. Since the sum as n goes from 1 to infinity of 1 over n, which remember we just wrote in a fancy way as 1 over the square root of n squared, right, diverges. Why? I could write it as p equals 1. I could write it as harmonic. I can write it as either of these two, right? It diverges. And we know by the limit comparison test that the sum as n goes from 1 to infinity of 1 over, I forget what it was, square root of 4n minus 1 plus 2n squared diverges as well. All right, I think I got you all the techniques. I know I got you all the tests. Tomorrow we'll start talking about some numerical methods for approximating sums of series that are convergent. Okay, hope you enjoyed it. I'll see you tomorrow, and thanks a lot for your time and attention.